Welcome to the E-Pathshala lecture series on computer science for postgraduate students. We are in the series of lectures on computer graphics and visualization we have been learning. It's going on very well, and let us look into the ninth session. So, we are in the ninth session of this lecture series on computer graphics and visualization. So, in this lecture we will look into more details about the important concept in 2D, that is line clipping, and where we have got two interesting algorithms. One is Cohen-Sutherland line clipping algorithm and Liang-Barsky line clipping algorithm. So, this session is going to be a very interesting session. Pay more attention, as this is an important topic as far as the 2D graphics is concerned. So, to start with, as we discussed in the previous lecture, we talked about point clipping, and then we proceeded to line clipping. It is similar to point clipping. Line clipping is just an extension of point clipping, where a line that is inside completely, that is if both the endpoints of the line are inside completely, the lines should be selected for display. If both the endpoints are outside and the line is completely outside, the line should be discarded. So, we have to make some tests. So, initially the algorithms actually make some simple tests to say if a line is completely inside or a line is completely outside, so can be discarded. Okay. So, the algorithms, for them to be more efficient, with few simple checks, they should be able to say that the line is completely inside, so selected, the line is completely outside, so discarded, and a portion of the line is inside and a portion of the line is outside, so intersections are required. So, an efficient algorithm should give us, with few checks, tell us the trivial reject and trivial accept cases. So, how a line clipping proceeds, as you can see here, there are various possible lines, and you see here for P1 and P2 is a line that is completely outside, both the endpoints are completely outside. For the case P7 and P8, while P1 and P2, P7 and P8 both have the endpoints completely outside, but line P1 and P2 is, even if the endpoints are outside, the line is also outside, but a portion of line P7, P8 is inside. So, for P7, P8 we need to calculate intersection points. At the most there will be two intersection points. So, there is either one intersection point, sometimes you would require to calculate for line P5, P6. For line P7 and P8 you will be calculating two intersection points. So, let us see the first algorithm, the Cohen-Sutherland line clipping algorithm, which is the rudimentary level procedure, and how Cohen-Sutherland algorithm solves this problem of, say, selecting lines that are inside and discarding lines that are outside. Cohen-Sutherland procedure conducts some initial tests to actually decide whether we need to go for intersection calculations or not. So, it is an efficient algorithm in that sense. So, with first few checks, it will be telling us whether the lines are completely inside or completely outside, and if intersection checks are really required or not. So, Cohen-Sutherland were very clever in actually assigning a 4-bit binary code, and which is called the region code for regions for regions around the clip window, that is and the window also as well, for regions around the clip window and also the region which is the clip region. So, Cohen-Sutherland have assigned a 4-bit binary code which is called the region code, that identifies the region around the central window, that is actually our clip window. If you look at this, what we see is a region, that is the central region is given by, is identified with a red bold line that identifies the central region, and that is actually our clip region. Okay. That is actually our clip region. So, whatever that lies inside this region will be selected, whatever that lies outside will be discarded. Okay. So, what are these codes here? There are 0 0 0 0 1 0 0 0. So, there are the whole region in and around the central clip window region is divided into 9 zones. Let me repeat, the whole region, the whole of the region around the in and around the central region, that is the clip window region, is divided into 9 zones. So, say this zone with the region code 1000 is the top, is on top of the central window region, the top zone. This is the bottom zone. 0100 is the region code for the bottom zone, 0010 is the region code for the right zone, 0001 is the region code for the left zone. So, there are 4 zones are identified. Now, 4 more zones are to be identified. So, this zone on the right corner is actually top right region with the region code 1010. This zone on the bottom left, bottom right corner is given the region code 0110. So, how did we give the region codes? How did Cohen-Sutherland gave the region codes? 4 bits are assigned. This is a binary code, as again as I said before, this is a 4-bit binary code. Binary code means there are only zeros and ones, and 4 bits only are there in the region code. So, what are the 4 bits? Each of the bits identifies one region. So, the rightmost bit, okay, the rightmost bit here identifies the left region, the next bit identifies the right region, the next bit, that is the third bit position, identifies the bottom region, the MSB bit, that is the leftmost bit, identifies the top region. So, left, right, bottom and top. So, you remember the sequence, the left, right. So, bit 1 left, bit 2 right, bit 3 bottom and bit 4 the top regions. So, that means for the central region, the region code is 0000, indicating that it is the central region. For the left region, the left bit is set, see 0001, the 1 indicates the left region. So, left, right, bottom and top. This is left to the central region. So, this bit position is set. So, that is why its region code is 0001. Here to the right region 0010 indicates that the right bit position is 1, that is set, indicating that the region code for this region is 0010. So, similarly, the bottom region has got region code 0100 and top region has got region code 1000. And now, the top right, bottom right and bottom left and top right regions are actually the OR operations of the neighboring 2 regions. Okay. So, ORing 0001 and 1000 gives you 1001, which is 1 indicates the top region, this 1 indicates the left region. So, top left region. So, this region code identifies uniquely a particular region around the central region, which is the clip window region. So, now why do we go for region codes and what is the fun in going for region codes? That is, what did Cohen-Sutherland do is, they took each endpoint for a line. So, take one endpoint for a line, identify its region code. So, take this other endpoint for the line, identify the region code. So, check if both the region codes for the 2 endpoints of a line are 0000, that indicates that the line is completely inside. So, our aim is to now compute region codes for a given endpoint. So, for line endpoints of the lines. So, we will be making some straight conclusions, or maybe we will be taking some obvious decisions by computing region codes for the line endpoints. So, how do we compute region codes for the endpoints of a line? So, if you see this again, this is the central region. Each bit position in the region code is used to indicate one of the 4 relative coordinate positions of the point with respect to the clip window. Bit 1 left, bit 2 right, bit 3 bottom, bit 4 top. So, now given an endpoint, say of the form x comma y. So, the line has got two endpoints, take one endpoint x comma y and take the x coordinate. What is that you do is, if x is less than x w min, make a check. If x is less than x w min, then set the left bit. So, take one position or one endpoint of a line, take the x coordinate, check if x is less than x w min, the left bit set if it is true. If it is false, reset it, that is keep it 0. So, set it only if this condition is satisfied. So, if x less than x w min, set the left bit. If x greater than x w max, set the right bit. Similarly, if y less than y w min, set the bottom bit. If y greater than y w max, set the top bit. So, if the condition is not satisfied by the x and y coordinates, then accordingly reset, that is keep that 0. Or then to check if x is less than x w min or if x is greater than x w max, what do we do is, because in computation in program you will not be actually checking the magnitudes of two values. Then to check the magnitudes of two values, what we can do is, we can check the sign of the difference operation, that is check if x minus x w min is less than 0, that means x minus x w min is less than 0, that is if the difference of x that is and x w min, if the difference gives the sign bit is set for the difference operation, then set that left bit. If the sign bit of the difference operation x minus x w min is set, then set the left bit. So, that is how for a given endpoint we can compute the region codes. See the bit 1 is set, bit 1 corresponds to the left bit. The sign of the difference operation x minus x w min, if it is set the left bit, otherwise reset. The sign of the difference operation x w max minus x, if it is set the right bit. So, bit 2 corresponds to the right bit, otherwise reset. The sign bit of difference operation, the sign bit of difference operation y minus y w min is set the third bit, that is the bottom bit. If the sign bit of the difference operation y w max minus y is set the top bit. So, or reset, else reset. So, that is how we check and identify a region code, a 4-bit region code for a given endpoint of a line. Now, that is how Cohen-Sutherland actually with for some trivial accepts and trivial rejects will be doing this. Now, take for example a line here whose region codes are given as, say that for both the endpoints the region codes are computed and the region codes are obtained like this: 0 1 0 0, 0 0 1 0 is the region code for the other endpoint of the line. Now, you see if you perform what is called a bitwise AND operation, if it is 0, that is what you get here is for a bitwise AND operation, you get bitwise AND operation, what you get is all zeros, isn't it. Similarly, take a line that is a vertical line, take a line that is vertical and is outside onto the right. Say its region codes are 1 0 1 0 and 0 1 1 0, 1 0 1 0 and 0 1 1 0. So, what does that convey is for this particular line, one bit position is commonly set, that bit position is the right bit position. Let me repeat that again. Imagine a line that is vertical and is to the right of the clip window region. So, its region codes, let us say, are 1 0 1 0 for one endpoint and for the other endpoint the region codes are 0 1 1 0. Now, if you take both the region codes, only one bit position, one bit is commonly set for both the endpoints, for the region codes of the endpoints, that is the second bit, that is from the right second bit. So, that bit position is the right bit position, and if you take bitwise AND operation, it results in a non-zero value. So, it results in a non-zero value. So, what is that we can conclude is, any line for which take the two endpoints of the line, and if one bit position is commonly set, and if you take what is called bitwise AND operation for both the region codes, and if you get a non-zero value, what we can say is the line is completely outside and can be discarded, and the line is a parallel line to the boundary represented by that bit position that is commonly set for both the endpoints. Maybe this is a big sentence, let me repeat. For lines that are outside and are parallel to either of the boundaries, for them one of the bit positions will be commonly set. Okay. That is, if the line is actually to the right of the clip window region and is vertical, assuming its region code is 1010 and 0110, in both the region codes, if you observe, one bit position is commonly set, and if you take bitwise AND operation for those region codes, it will result in a non-zero value. So, what do we say is take bitwise AND operations, and if it results in a non-zero value, we should assume that the line is completely outside and is parallel to that boundary represented by that bit position which is commonly set. So, here the line is a vertical line and is on to the right, because right bit position is commonly set and is outside and can be discarded. So, with just by checking the region codes of the two endpoints, we are able to conclude the line is inside or outside. So, similarly, compute the region codes for both the endpoints. If you get 0 0 0 0 for both the region codes of the endpoints, we can confidently say that the line is completely inside and can be selected for display. So, such trivial checks are to be trivial conclusions are to be taken, and the region codes are very helpful in that case. So, if none of the checks are satisfied, that is both the region codes are not 0 zeros, and after taking the bitwise AND operation you are getting say a 0 value, then we should be calculating the intersections for sure, because the line is assumed to be actually cutting through the window boundaries, and a portion of the line is inside and should be calculated for what portion of the line is inside. So, for that we need to do intersection calculations. So, for performing intersection calculations, we can take the slope point form of a line. What is the slope point form of a line? Point slope form of a line. The intersection points with a clipping boundary can be calculated using the slope intercept form of a line. That is, we know that slope can be calculated by this equation, m is equal to y2 minus y1 by x2 minus x1, assuming x1 y1 and x2 y2 are the two endpoints or the two endpoints for a line. The y coordinate of the intersection point at a vertical line. See, for a clip window, for the two vertical lines, so the clip window is made up of 4 infinitely extending lines. The clip window is made up of 4 infinitely extending lines. For the two vertical lines, say for example, if a line is coming from outside and is intersecting a vertical line, so for this at the point of intersection, you need to just compute only the y coordinate. You don't need to compute basically the x coordinate. Why do we need to compute only the y coordinate? Is because for the vertical line we know the x coordinate of the vertical line, that is xw min or xw max, isn't it? There are two vertical boundaries that make up the clip window. Assuming a line from outside is cutting through the vertical boundaries of the clip window, at the point of intersection you need to compute only the y coordinate. You need to just calculate only the y coordinate, because x coordinate is either xw min or xw max, because that makes up the two vertical boundaries. So, the equations here show that the y coordinate of the intersection point at a vertical boundary is given by the equation y is equal to y1 plus m into x minus x1. We know this equation from y minus y1 is equal to m into x minus x1 from the slope point form, and for x, because y1 is known and m is known, x1 is known, then what is this x? For x you substitute xw min or xw max depending on which of the boundaries the line is intersecting. Okay. Sometimes it might intersect both. So, once you substitute x w min and next time you can substitute x w max, you will get two intersection points. Okay. So, the y coordinate of the intersection point at a vertical boundary is given by this equation. Okay. Similarly, when a line from outside cuts through the window and enters the window region cutting through horizontal boundaries, what is that you can do is at the intersection you need to calculate, this is a horizontal boundary, there are two horizontal boundaries for example. So, a line from outside cuts through one of the horizontal boundaries and enters the inside. At the intersection you need to calculate only the x coordinate, because the y values are known, which is either y w min or y w max for the y boundaries of the clip window. So, the y coordinate is known at the intersection point and the x coordinate only needs to be computed when a line intersects the two horizontal boundaries. How do we compute the x coordinate of the intersection point when a line intersects the horizontal boundaries? Is by this equation. We rewrote that equation for x, that is the only difference. In the previous case you take in the case of y, now we need to compute x. So, take y 1 onto the other side, divide that with m, and x 1 to be taken on the other side, it becomes a plus. So, x equal to x 1 plus y minus y 1 by m, where y is the unknown parameter. So, if you want to compute intersection of the line with the top boundary, substitute for y w max. If we want to compute intersection with the bottom boundary, substitute for y w min. So, that is how we perform intersections. In this example, there is an example to explain this Cohen-Sutherland algorithm, and see this, it is actually there are on the right you can see that the window boundaries defined by 4 infinitely extending lines, x equal to 1, x equal to 7, y is equal to 2 and y is equal to 6 are the 4 infinitely extending lines that make up the clip window region. Okay. Given a line with endpoints p 1 0 0, p 2 8 comma 5. So, given two endpoints for the line p 1 0 0, it is extending from 0 0 to 8 comma 5. Now, what do we do is we first start with the left boundary, find the intersection of the line with the left boundary, then go to the right boundary, then go to the bottom boundary, then go to the top boundary, find all intersections, and then we discard all the portions that are outside, and we will be taking only the final portion of the line that is actually inside. See, these lines are infinitely extending lines. Again let me repeat, the window is made up of 4 infinitely extending lines. So, any line that cuts through the window region, obviously any bigger line obviously cuts through the left boundary, bottom boundary, top boundary and right boundary and so on. So, at the most there will be 4 such intersections that we will be computing, because one with the left, one with the right, one with the bottom, one with the top for a longer line. So, take a longer line and at the most how many intersections you would be calculating is 4, but out of which only the 2 intersections are actually the intersections with the clip window region, and the line that lies within that intersections only to be selected for display. So, you will get 4 intersections, out of which you need to take only the 2 intersections that actually are the intersections with the clip window region. So, we start with the we start computing the region codes. The region codes for the position 8 5 is say 0 0 1 0. The region code for the other 0 0 position is say 0 1 0 1. Now, taking bitwise and you are actually getting 0 0 0 0, all zeros. So, you are not sure, none of the region codes are, that is 0 0 0 0. So, we will be going for intersection. So, you cannot have trivial accept, you cannot have trivial reject. So, we have to compute the intersections. So, compute m first. M is nothing but y 2 minus y 1 by x 2 minus x 1, and now a 5 by 8, m is actually 5 by 8. take the left, start with the left, then go to the right, then go to the bottom and then go to the top. First find the intersection of the line with the left boundary. So, left boundary is actually vertical boundary, left is represented by the vertical boundary x equal to 1. So, for intersections with vertical boundaries, we need to compute only the y coordinate of the point of intersection. The x coordinate is actually 1, x equal to 1, the x coordinate is 1. The y coordinate of the point of intersection with the left boundary is given by the equation. You can use the equation that we took before, y is equal to y 1 plus m into x minus x 1. So, y p, y dash, y p, you can take y p or whatever, y 1 plus 5 by 8 into 1 minus 0, it is 5 by 8. So, p 1 dashed is the first intersection with the left boundary whose coordinates are 1 comma 5 by 8. Now, with the right boundary compute the intersection, with the right boundary compute the intersection, what is that we do is take the same equation, because right boundary is a vertical boundary. At the intersection point, the y coordinate of the point of intersection is actually to be computed, the x coordinate is known for the right boundary. Okay. So, the right boundary is represented by the line x equal to 7. So, the x coordinate is known for the intersection point, only the y coordinate needs to be computed. So, use the equation for y is equal to y 1 plus m into x minus x 1, for x substitute 7. Earlier we substituted for x 1, now you substitute for x 7. That is the only difference between the previous and the current equations. So, y 1 is 5 by 8, already we have computed a y 1 5 by 8 plus 5 by 8 into 6, you get 35 by 8. So, the p 2 dashed here gives us the intersection point 7 comma 35 by 8. Okay. Now, we got 1 comma 5 by 8 as one intersection point, 7 comma 35 by 8 is the other intersection point. Now, with the bottom boundary compute the intersection points. Now, bottom is the y coordinate of the intersection point, bottom is a horizontal line, the y coordinate of the point of intersection is now known. It is just enough that we compute the x coordinate of the point of intersection. So, the x coordinate of the point of intersection can be computed by x is equal to y 1 plus y minus y 1 by m plus. So, if you remember the equation, so this is the equation x 1 plus y minus y 1 by m. So, x 1 plus y minus y 1 by m for the bottom boundary. So, what is this x 1 here? X 1 here is the already computed line, already computed point position, the 1 plus already computed position is 1, okay, 1 plus y minus y 1 by m, y is 2 for the bottom boundary, 2 minus 5 by 8. So, what is the 2 minus 5 by 8? Y minus y 1 by m, okay, 2 minus 5 by 8 multiplied with 2 minus 5 y minus y 1 by m is given here, which is computed again to 16 by 5. So, for the intersection of the line with the bottom boundary, the y coordinate is 2, which is known, which is y is equal to 2. The x coordinate is computed using the equation x 1 plus y minus y 1 by m by substituting for y w min. So, we got 16 by 5. And finally, the top, because the top it is inside. So, check with respect to the top boundary, the point 7 comma 35 by 8, which is the intersection point, and p 2 8 comma 5 both are actually inside points. So, you do not have to compute any intersections further. Yeah, with respect to the bottom boundary, if you perform intersection, as we got the p 1 double dashed. So, we started with the left boundary intersection, which is p 1 dashed, then we computed the intersection with the right boundary, which is p 2 dashed, then we computed the intersection with the bottom boundary, which is p 1 double dashed, where we got 16 by 5 comma 2, and finally, when it comes to the top boundary, the top boundary, it is p 2 and p 2 dashed, and all the whole of the line is actually is within the top boundary. That is, if you imagine an infinitely extending top boundary, the entire line is within the top boundary, it did not cross the top boundary. So, we do not have to actually compute the intersection of the line with the top boundary. Okay. So, for the top region P1 double dashed is inside, P2 dashed is inside. So, terminate. So, when we compute P2 dashed, P2, P1 double dashed and P1 dashed and P1, everything is actually inside the top boundary. So, we need not calculate the intersection of the line with the top boundary. Okay. So, finally, how do we conclude this is when we compute intersections, we get double dashed and triple dash. If we go for that, the most there are 4 intersection points. Now, as I said, there will be maximum of 4 intersection points. We need to bother only about the 2 intersection points that actually cut the clip window region, which is inside region, the exact region. So, we are interested in only the line part between P1 double dashed and P2 dashed. The line part between P1 double dashed is inside and P2 dashed is inside. So, that is the end of it. So, discard the portion, remaining portion of the line, that is outside P1 dashed and outside P2 dashed. So, that is P2 to P2 dashed and P1 dash to P1 dashed, P1 double dash to P1 dashed and P1 dash to P1. The entire line can be discarded. So, consider only the line between P1 double dashed and P2 dashed. So, how did we go with is we took the endpoints of the line and we computed the region codes for both the endpoints, and then we checked whether we can go for a trivial accept or trivial reject. None of the cases have worked. So, we had to compute intersections and calculations are to be taken up. So, we started with the left boundary, computed the intersection of the line with the left boundary, then we computed the intersection of the line with the right boundary, computed the intersection of the line with the bottom boundary, and we understood that the line is not crossing the top boundary. So, we do not have to compute the intersection with the top boundary, and we got finally 2 positions between which the line is actually inside the clip window region. So, that is how we perform intersections, and we take all the 4 regions in order and perform intersections, all the 4 boundaries in order and compute the intersection points. So, this is how we can solve a problem using Cohen-Sutherland line clipping procedure. You can try other problems taking trivial accept cases, trivial reject, and taking other intersections. You can try simple problems based on this. An example problem is solved here. You can try other problems. In this module, what we have learned is we have learned how line clipping is done using Cohen-Sutherland line clipping procedure, which is a very rudimentary level procedure where region codes are being employed, and for every endpoints we perform region codes and we compute region codes and go for trivial reject and trivial accept, and finally compute intersections using simple slope point form equations using the line equations. So, this is what we have learned in this module. Hope this has been useful to you, and it is self explanatory. If you solve more problems on this, you will be able to appreciate and take up more such similar problems. Okay. So, let us conclude this session with this, and in the next class we will look into the 3D part with this, because the clipping part is over, a major part is over. We will look into the 3D object representations, which is an interesting topic to follow. Thank you.